Pyridine. Pyridine is an example for a six-membered aromatic heterocyclic compound. Here is the structure for pyridine. And this structure is similar to the structure of benzene, where one of the carbons have been replaced by nitrogen in the case of pyridine. So this is the structure for benzene, and if one of these carbons right here will be replaced by nitrogen, then it's going to become pyridine. And in pyridine, these electrons that is present on nitrogen will not be taking part in delocalization, because these are present in an sp2 orbital, which is perpendicular to the p orbital. Let's see why pyridine is aromatic. Pyridine follows all the rules for it to be an aromatic compound. Say, for example, it is cyclic, and all of these atoms right here are sp2 hybridized. It falls under the category of 4n plus 2 system, okay, obeying a Huckel's rule. And here, the total number of electrons that is participating in resonance is 6. So therefore, if we are going to put n equals 1, the equation will be solved. So all of this is going to make pyridine an aromatic compound. When we compare the acidity of pyridinium ion with that of the typical ammonium ion, we can say that the pyridinium ion is more acidic. Why? Because here the hydrogen is connected to an sp2 nitrogen, which is more electronegative. But in the case of pyridinium ion, or in any typical ammonium ion, this nitrogen is sp3 hybridized, which is comparatively less electronegative than the sp2 nitrogen, and therefore it will be harder to pull the hydrogen here. Okay. Since it is more electronegative, in the case of pyridinium ion, this hydrogen can be lost easily. Pyridine can react as a typical tertiary amine. Say, for example, it can undergo an SN2 reaction with an alkyl halide, where these electrons that is present on nitrogen will go and make a nucleophilic attack on the electrophilic carbon and give the substitution product. Let's draw the resonance contributors for pyridine. In pyridine, we said that these lone pairs that is present on nitrogen will not be taking part in delocalization, right? So we are not going to push those electrons into the ring. Like benzene, pyridine is also going to have an uncharged identical resonance contributor, for which you are going to relocate the electrons from the pi bond. Since nitrogen is electron withdrawing, we are going to push these electrons to form the carbocation. Since this is the carbon that is losing the electrons, we are going to put a positive charge on that carbon. Now, as we shift the electrons from the pi bond, this carbocation is going to switch around the molecule. Let's shift these pi electrons here. So that's going to give us another carbocation, since this is the carbon that is losing the electrons. Now again, for the last resonance contributor, we are going to shift these electrons here. So now it will be this carbon's turn to have the positive charge. So here are the resonance contributors of pyridine. And as you can see from here, these are identical to what we have seen in the case of benzene. And these resonance contributors are brought in because of the electron withdrawing nitrogen atom.